What's up, AP Physics C Mechanics students? Welcome back to our elegant physics videos. Today's topic 2.10 circular motion part 4. So let's jump right in. Acceleration of a swinging pendulum. So the pendulum basically consists of a small mass connected to a vertical light thread or string. Thus, this system forming a simple pendulum. The equilibrium position is when the string is along the vertical line. So technically, the equilibrium position will be this point. During the downward motion, the object is speeding up and has both accelerations, centripetal and tangential. The tangential acceleration has the same direction of the velocity, and this is applicable for the downward motion. So, for example, here, when the object is moving down, there will be two types of acceleration, the centripetal acceleration AC and the tangential acceleration AT, and the tangential acceleration is the same as the direction of motion or the direction of the velocity. Now, during the upward motion, the object is slowing down and has both accelerations, centripetal and tangential. The tangential acceleration has an opposite direction to the velocity. So let's assume that this mass is moving downward. So the direction of motion is toward this direction, which means the tangential will be, uh, the direction of motion is in this direction. It's going up, which means it's slowing down. To slow down the object, we will need to apply the tangential acceleration, and the direction of the tangential acceleration should be opposite to the direction of the velocity, so we'll be acting in the opposite way. However, for the centripetal acceleration, it will be always toward the center. And as a result, the net acceleration will be acting in this way. At the equilibrium position, the object is not gaining speed anymore. So at the equilibrium position, we will have the maximum speed. So the tangential acceleration, it becomes zero, and there will be only centripetal acceleration acting here. At the extreme position, the object has only tangential acceleration. And this is because at the maximum position, and I mean by the maximum position at the extreme points here and here, the object will stop momentarily. So at these two locations, the speed becomes zero. And if we apply the formula AC is equal V squared over R, since this is zero, then the acceleration, centripetal acceleration becomes zero. However, here we have acceleration, and this type of acceleration is tangential acceleration. So at the equilibrium, we have only AC, and there is no AT because we have obtained or achieved the maximum velocity. Loop de loop. A car is traveling inside a vertical circular track. Through different points across the inner circular track, forces acting on the track have tangential and centripetal acceleration. Again, this is circular motion, so you should expect to have centripetal and tangential acceleration. However, we will only consider forces along the centripetal direction or the radial components. Now, although here we have two types of forces, particularly at point A, but we're going to consider only the forces that are aligned with the centripetal direction. Actually, here at point A, we have two forces are aligned with the radial direction or the centripetal direction. We have the force of gravity and the normal push. Remember, the radial direction or the centripetal direction is the direction where it's aligned or coincide with the radius of the circular path. Now at point B, the force of gravity always perpendicular like this, and we won't be able to consider it because it's not aligned with the radial direction. Only the normal push perpendicular to the path, and it will be aligned or pointing toward the center. So this can be promoted into centripetal acceleration or centripetal force. Now at point C, we have two forces acting on the object. We have the force of gravity, which is acting downward. So assuming that the car now is in the inner surface of the loop and the normal push acting downward. Now here in the point D, due to the symmetry with point B, we can say that the force of gravity is no more aligned with the centripetal direction, only the normal push is aligned with the centripetal direction. Now for the first case, the net force for the centripetal forces are Fn and Fg. Since Fn is up and Fg is down, the Fg with a negative sign, and these two forces are equal to the mv squared over r, or let's say the difference between these two forces is equal to the mv squared over r because the difference represents the centripetal force, and the centripetal force always equals to the mv squared over r. In the second case, we have only one centripetal force, or let's say the centripetal force here in this case is equal to the normal push, and we can write safely that Fn is equal to mv squared over r. Here both forces are acting downward, so the addition of these two forces, the net of these two forces is equal to centripetal force, which means they are equal to mv squared over r. Again, here we have single force acting inward, and this is should be promoted into centripetal force, and we know that the centripetal force is equal to mv squared over r. That means Fn is equal to mv squared over r. Now, exercise 1, the figures show a cart moving over the top of the hill. This is case 1, moving at the bottom of the dip. So this is case 2, and moving at the top of the vertical loop. This is case 3, and you can notice that the cart is flipped upside down because it's moving in the inner surface. In each case, the normal force acting on the cart Fn and the weight. So here in this case, for example, the normal push is acting downward and the force of gravity, sorry, the normal push is acting upward. This is Fn, and the force of gravity is acting downward. Here we have the force of gravity is acting downward, and the normal push is acting upward. And here, both of them, the force of gravity and the normal push are acting in the same direction. In which case, it is always, or is it always true that Fn greater than Fg? And in which case, is it always true that Fn is less than Fg? Now let's break down the cases and let's take each case individually. Now here, in all of the cases, we will have centripetal acceleration, which means we will deal with centripetal force. Now the centripetal force is actually the net force acting along the centripetal direction. Now, so obviously that the centripetal force should be acting here downward, which means the net force should be downward. And to make the net force directed downward, we must have the downward force greater in magnitude than the upward force. And always in this case, the normal push here, the normal push is less than the force of gravity. So this is for the first case. In the second case, here, the Fn is and the Fg, both of them will give us the centripetal force. So the centripetal force, which is the net force acting along the centripetal direction. Now, since the centripetal force is acting upward because it's always should be drawing toward the center and the center is here. So this is the Fc or the net force. And in order to make the net force toward the center, we must have the normal push greater than the gravity. So here in this case, the normal push greater than the gravity. Now for the last case, one can never know whether Fn or Fg is the greater because both of them will make up the centripetal force. So the addition of both of them will give me the centripetal force. But with this information, one can never know which one is bigger than the other. So it's not always to be true. So case 2 always gonna be Fn greater than Fg. And this can be found in here or maybe here. However, for case 1, we have the Fn is less than the force of gravity, which means the force of gravity always greater than the Fn. And it can be found here, so the correct answer would be B. The minimum and maximum speed of circular tracks. In circular tracks, like a roller coaster going over a hill, the normal push Fn is the indication whether the track is safe or not. If the normal push drops to zero, then the object in motion will lose contact. We anticipate that for a roller coaster, we would require minimum speed to cross the vertical track. And for the hill, there is a maximum speed that should be not exceeded. So let's take the first case at the top of the roller coaster. So let's assume this picture shows only part of a roller coaster. And here the cart is flipped upside down. The two forces acting here are the normal push and the force of gravity. The net force of these two forces will make up the centripetal force. Now the centripetal force is mv squared over r, and since both of them are indicate the same direction, so the summation of these two forces is the centripetal force. So Fn plus Fg is equal to mv squared over r. Now let's isolate Fn because here we are interested in finding the contact force and normal push, one of the important contact force generated by surface. Fn is equal mv squared over r minus mg. I just moved the fg to the other hand side and then I unpacked the fg into mg. Now going on top of a hill, so here the object is moving in the outer surface of the hill. Now we know that there will be two forces, force of gravity and normal push. And knowing that here always the force of gravity will be greater than the normal push. Now consider the positive direction to be inward, and minus Fn plus Fg equals mv squared over r. We do the same assumption always. The inward direction will be positive, the outward direction will be negative. And we're going to consider the Fn because we are looking for an expression for the contact force between the surface and the body. Moving Fg to the other hand side, so it becomes minus, and then multiply both sides. Let me explain it more. So what I did here, we just move the Fg to the other hand side, so it becomes minus. So minus Fn equals mv squared over r minus the force of gravity, which is mass times gravity. Now multiply both sides with minus. So minus times minus is a plus. Minus times mv squared is minus mv squared, and minus times minus mg is plus mg. So at the top of a roller coaster, the normal push is written in this way. And when we go at the top of the hill, it's going to be mg minus mv squared over r. At the top of a roller coaster, so Fn and Fg are acting downwards, and we found that Fn is equal mv squared over r minus mg. If we start losing contact, and this is the unpreferable or favorable, let's say, case, then the normal push becomes zero. So here we are looking for the limitation of this kind of motion. Now, if we lose the contact, then zero is equal mv squared over r minus mg because there is no more normal push. And let's solve it for v. We cancel m and m because if we move mg to the other hand side, it becomes mg equals m v squared over r. Now mass with mass cancelled out. We move r to the other hand side, it becomes rg equals v squared. Taking the square root for both sides, and we will get that the velocity is equal square root of rg. Now, what does this formula represent? This represents the minimum possible speed in this track that if we exceed it, if we have less than the speed, then the object will lose the contact. So this is the minimum possible speed. And then the minimum possible speed required for crossing the roller coaster is v minimum equals square root r times g. Now, and this is what will happen if we have this velocity or greater than this velocity. Because you can understand that if we have less than this velocity, the object won't complete the path, so it will slip backward, or it will lose the contact at some point and then it will fall down. So to guarantee that the object will maintain on the same path, we should apply this minimum speed, r times g. You can figure out that this relationship is totally independent of mass. It's only related to the gravitational field strength and the radius of the circular path. Now going on top of a hill, so the forces are acting here again, force of gravity and normal push. Now let me add the normal push here. We have normal push, and obviously that the normal push here in this case is less than, in magnitude, less than the force of gravity because the centripetal force is acting downward, and we know that the centripetal represents the net force along the centripetal direction. So in order to make the net force toward downward or acting downward, we must have the gravity bigger than the normal push. Now considering that the positive direction to be inward, so the force of gravity is positive, the normal push is negative, equals mv squared over r. Now let's solve it for the normal push, and this is what we got. Now if we start losing contact, then the Fn is equal 0. And 0 is equal mg minus mv squared over r. So by moving mv squared over r to the other hand side, it becomes mv squared over r equals mg, mass with mass cancelled out. So v squared is equal r times g. And again, the velocity becomes rg. But what do we call this velocity? This is the maximum possible speed allowed for going on top of the hill. So what will happen if we exceed this speed? Then the object will lose the contact and it will fly away from the surface. So here in this case, we have exceeded the speed, which is the square root r of g. Some useful remarks. Going inside a roller coaster of a very large radius would increase the minimum speed. As you can notice here, this relationship is totally independent of mass. So if we have big R, the minimum speed will be bigger. And this minimum speed required to pass safely without losing contact. Now going over a hill with a very small radius or narrow hill, that would decrease the maximum speed. So narrow hill with a very small radius, so the radius here, if we consider this is the circle, this is will be the radius, and very small radius means the maximum speed, the smaller the radius, the smaller the maximum speed. Okay. Now exercise 2. A sphere on the end of a string is released from rest at point X. So we release the object from here. This is the pendulum problem. And it swings through point Y to point Z. Point Y is the lowest point for the sphere as it swings. So at point Y, we will assume it to be the equilibrium point. The air resistance is negligible. Four directions at point Y are indicated as I, double I, triple I, and IV, and this is what we found here. This is I, which is acting upward, to the right, double I, downward, triple I, and the IV is to the left. Which of the following best indicates the direction of the acceleration of the sphere at point Y? Remember that the acceleration, when I say the term, the direction of acceleration, I mean by that the A vector, which is consists of AC and AT. This is considered to be circular motion. Now we know that at the equilibrium position, the tangential acceleration becomes zero because the velocity here is maximum. Only AC will be acting here, so the direction of acceleration will be indicated by the direction of the centripetal acceleration. And we know that the direction of the centripetal acceleration will be acting always upward, and this is also the direction of the A vector. So I is the correct answer. A cart of mass capital M is approaching a hill with a circular top of radius r, as shown in the figure above. The cart is carrying a load of mass m, so the mass of the load and the mass of the cart is the same, and it's traveling with a speed v0. When it is at the top of the hill, the length of the cart negligible in comparison to the radius of the hill. The cart never loses contact with the hill surface. The cart and the load can both be considered to be at the same position. So there is no relative motion between the cart and the load. The speed v minimum is the minimum speed necessary for the cart and the load to leave the surface of the hill. At the top of the hill, if the load is removed, so what will happen if we remove the load? What is the new minimum speed necessary for the car to leave the surface of the hill? We know that the minimum speed, we have derived it in the previous section, is equal to the r times g. So, as you can see here, the formula is totally independent of mass. So even if we increase the mass or reduce the mass has nothing to do with deciding the value of the minimum speed. So you should expect to consider the same minimum speed before removing or adding the mass. And the correct answer is C. A cart of mass again is approaching a hill with a circular top of radius r. Now, we have the same information as before. The cart and the load can be considered to be the same position. And a free body diagram showing all the forces and not components acting on the object at the top of the hill, how many vertical forces will act on the cart and how many vertical forces act on the load. So let me make a small picture for the load and the cart. Let's consider the load first. Regardless of the position of the object on the hill, the forces acting on the load are first the force of gravity, And we have the normal push because we have a contact between the load and the surface of the cart. Here we are considering only the load. So we have only two forces acting on the load. So let me write here too. Now, what about the cart? So this is the cart. So first of all, we have the force of gravity on the cart. We have the pressing force because of the load. So let's call it FP, pressing force. So the load is pressing by its weight on the cart. And we have the normal push between the surface of the track and the wheels. So we'll have normal push upward. Now, in total, we will have three forces. So three forces on the cart and two forces on the load, which means the correct answer will be C. A ball of mass 0.4 kilogram is attached to light rope of length 1 meter. The ball is moving in vertical circle as shown in the figure. With Earth gravitational force as the only force external to the ball string system, the speed of the ball at the point P is 5.4 meter per second. So this is point P, and we have information about the speed here. The acceleration, when I say the acceleration, I mean by the acceleration, the ACT squared and the AT squared of the ball at point P is mass nearly. So first we need to find the AC, and the AC can be calculated via this formula V squared over R. Know that at point P the speed is 5.4 and the radius is the same as the length of the rope. Because the length of the rope is 1 meter, also the radius will be 1 meter. So as a result, the final answer for the centripetal acceleration is 29.16 meter per second squared. If this is not enough, we need to see if the tangential acceleration is existed or not. Now, to find the centripetal acceleration, actually we have different ways. We can use alpha times r, however, or r times alpha, but here we don't have alpha. So the best way to find the tangential acceleration is by considering or by applying Newton's second law along the vertical direction. So along the vertical direction, we have the force of gravity acting on the ball, nothing else along the vertical direction. And we know that the tangential acceleration is acting along the vertical. So because it's always tangent to the path, so we just write F net along the vertical direction. F net is equal M times A tangential. So the F net is only force of gravity multiplied by MAT. Force of gravity is MG multiplied by MAT. So actually, the AT is just the gravity. So it equals to G, which means it equals to 9.8 meter per second squared. So we have now the AT, we have the AC, we just plug them here to get the final answer. The AC is 29.16 squared plus the 89.8 squared. And the final answer for the magnitude of the acceleration at point B is equal approximately 30.7 meter per second squared. The closest answer to my answer would be D. So D is the correct answer. A car A can travel around the curved section of a road without skidding at a maximum constant speed 10 meters per second. So this is the maximum possible speed before we lose the contact. If we exceeded the speed, the object will lose the contact and it may fly. When car B travels around the same curve without skidding at its maximum speed, it has twice the centripetal acceleration as the car A. Now, the maximum speed at which B can safely travel around the curve is most nearly. So here we have information about the centripetal acceleration, and we count the term twice. So you may use the factor of change to solve this problem. Now we know that the centripetal acceleration is equal V squared over R. So one can say that the V is equal. If we move R to the other hand side, we took the square root, it becomes ACR. Now let's apply the factor of change here. We have double the centripetal acceleration and the radius maintain the same because we are using the same path. So we should expect that the factor of change of the speed will be radical 2 multiplied by the original minimum speed. Now the original minimum speed is 10, and the final answer is 14.14 meter per second. So remember, this technique will give me the factor of change that if we multiplied with the previous or original value of the speed, it will give me the new value. So here, this technique will give me only the factor of change. So the answer is only radical 2. But this radical 2 must be multiplied with the original velocity, which is 10 meter per second. And this is what I did. So the final answer is 14. In the figure shown, a small object of mass m is spinning in a nearly horizontal circle of a radius r at a constant speed v. The magnitude of the horizontal net force on a small object is F. The object is stopped, and then starting from rest, the object is made to spin in a nearly horizontal circle of radius r so that it is speeding up with acceleration a. Which of the following expression is correct for the new net horizontal force on the object? Here, in this situation, we have circular motion. So technically, we will deal with centripetal acceleration. And since we are speeding up in the second trial, we will have tangential acceleration. You can notice that these two acceleration are on the horizontal plane. Because the path of the circle is in the horizontal plane, this is the plane. And to draw a tangent to the path, you must place your tangent at the same plane or on the same plane. So AT is horizontal and AC is horizontal. As a result, we once can say that we will have a horizontal force acting here toward the centripetal direction. And we have another force acting at the tangential direction. I will call it FT. FT means tangential direction. So remember, the centripetal acceleration will generate the centripetal force, and the tangential acceleration will generate the tangential force. Now, how we can find the centripetal force or centripetal force. Now, for the centripetal force, this force is the tension, and from the previous case in trial 1, before we repeat the experiment, this force, it was F, because this is the only force applied here, especially that the speed was constant. So when the speed is constant, there will be only centripetal acceleration. And within the centripetal acceleration, the centripetal force will be generated. This centripetal force is toward the center, and the centripetal force here is represented by the tension force. So here, the tension force will appear again, and it will be promoted to the centripetal acceleration. So actually, the centripetal acceleration is the tension, and they denoted by F. What about the tangential acceleration? To find the tangential acceleration, we just apply the Newton's first law on the tangential direction. We have only one force acting on the tangential direction, which is the Ft, and it can be calculated via n times the acceleration tangential. Now, since the tangential acceleration and the centripetal acceleration are always and forever perpendicular to each other, then the tangential force and the centripetal force also will be perpendicular. And now we can combine them. Since they are perpendicular, we can combine them using the Pythagorean sum. So to find the net horizontal force, we just combine the two forces together. Now the first force is the F, the second force is MAT, and this is the net of the horizontal force. So the correct answer is A. Now, if we want to determine the direction of this force, the direction of this force will be the same as the direction of the acceleration. The acceleration will be in this way, as well as the magnitude, or let's say the direction of the force, of the net force of the horizontal forces. And that's it for today's lesson on 2.10 circular motion part 4. Thank you for joining me. See you next time.